Hi, I'm Niladri. I'm a PG student at UCL, and I work very closely with Adobe. And this was a project I did during last summer's internship there. Also, thanks to Voxel 51 for inviting me to give this presentation. Uh, so, uh, Typically for representing 3D shapes, we have two very popular representations. One is voxels, and another is with meshes. And the problem is that these are typically built for classic rendering purposes. But the problem is that with level of detail, it means that the more number of faces you have in case of a mesh, the higher is the level of detail for that. But this is a problem when it comes to autoregressive generation, because it essentially means that more the number of tokens, more is the uh, high quality of generation. So you do not want necessarily higher quality of generation with higher number of faces, which in this case is higher number of tokens. And you can see that this will quickly explode since attention is actually quadratic complexity. So in this case, for voxels, which is this popular paper called OptGPT, which uses octrees, it actually takes a huge number of tokens to represent an object. So this is what we want to fix. And instead of following level of detail, which is the convention in geometry, we suggest level of semantics. It essentially says that instead of trying to have this hierarchy with higher number of faces, we are going to get there semantically in an increasing way. And it means that we are not trying to exactly represent the same object, but we are trying to represent the object in a semantically similar way. So for example, in the left, you see this penguin, right? And there is this adult penguin and there's this baby penguin. If you have a very limited budget of, say, 4 tokens, you can perhaps say that it might be better to ignore the baby penguin completely and get a complete shape right than rather trying to fit in that baby penguin somehow and get a very awkward shape, which you see in this case of both when you do this with level of details, both for octrees and meshes. But you see there's this slight bulge when trying to represent the baby penguin when you have a low budget of tokens. And we see the similar when we are trying to represent London Bridge in this case, where we have a very low number of tokens, you will see that the bridge actually looks very different. But semantically, it is actually similar. It's still a bridge. It's not an apple or something else. And the difference between 16 and 64 is that the difference in the art, which you see at the bottom. So these are the uh, like the little bit of quirks that we want to capture when we go in a semantically increasing order. And why level of detail is a bad fit for AI generation is that since this was designed for rendering and compression, we do not want this higher number of tokens when we want to generate objects in an AR way. And it also means that if uh, early prefixes are long, it's actually very hard to recover because if you're generating a very long mesh with, let's say, 100,000 faces or 200,000 faces, if the AR model makes mistakes somewhere along the line, this mistake will be propagated throughout. So we want to make these prefixes as short as possible, and we want to extract shapes from a varying number of prefix. So in this previous example where you see where we go from 1, 4, and 16, we keep the prefix the same. We are only appending tokens after that prefix. So if you, for example, take this object with 64 tokens, the first token is the same which you see for the example with 1 token. We are only appending here. So we want to order tokens by semantic salience. And what we want is that it should decompose to a complete and recognizable shape, even though it looks very different when it comes to geometry. And we want these early tokens to capture principal semantics, and the later tokens will add instance level detail, which makes the geometrically closer to what we want to go. And the advantage is that it takes a very low number of tokens compared to previous methods, from as low as 0.1% to 10% of tokens. So coming to the method, it all starts with a VAE representation. And in this paper, we show our method with two different VAE representations. We both show this both with direct 3D and also with trellis. So you can take any shape you want and then pass this through a 3D VAE, such as trellis or direct 3D, and then you will get the latent representation of that object. So the first step is you have the object, you take the point cloud, and then pass it through the 3D VAE to get the latents in. And now once you get the latents in, then our method comes in. So our method is actually agnostic to whatever VAE representation you choose to use. The results I will show in this paper are mostly with direct 3D, but we also have some results with trellis in the paper. So once we have these latents in, we're going to pass this through a causal VIT encoder. And this will give us a 1D tokenization. So, so the typical shape latents are in the form of 3D vector. So we are going to patchify them with a VIT encoder and make it a 1D tokenization format. And to this, we are actually appending some register tokens. So the concept of register tokens comes from this paper a few years back, which suggested that that a lot of the space in the VIT is actually wasted, and the VIT actually uses an internal scratch pad for doing some of the intermediate computations. So to get this ordered representation, we are using a VIT encoder with the shape latents as input, and we are appending some register tokens. And to this tokenization, we are actually performing nested dropout. And this nested dropout essentially means that at first, let's say it is keeping one token, next it might keep 4 tokens or 16 tokens or 64 tokens. So the first few tokens are always kept. And this is how we actually get the most of the information to shift to the earlier tokens. Since the first token is always kept, the encoder, while trying to encode this latent representation, will always try to push as much information into the first token as possible, and then the second token and the third token and fourth token and so forth and so on, so that when we decode this, we are going to get semantically closer to what we want to get to. And these register tokens are the ones which is actually kept, and the initial set of tokens are actually thrown out. And once we have this nested dropout, we are going to keep a certain prefix of tokens. And these tokens are actually used to condition a generative model. So once we do the nested dropout, we are only keeping, let's say, 1 token or 4 tokens, which is actually used in the generation process. But we actually need to recover the full set of tokens for the VAE to actually decode them back. And to do this, we are having a generative decoder. And this is essentially a DIT, which is a diffusion transformer. So conditioned on these tokens, we are going to generate the full set of tokens with a generative model. And this is performing simple flow matching. And once this flow matching is done, we are going to generate the full set of tokens from, let's say, a single token or 4 tokens or 64 tokens back to the entire set of 512 tokens. And a lot of this concept of nested dropout and this generative DIT decoder, which is this asymmetric structure, is influenced from the paper called FlexTalk, which tries to do this with images. And they have this kind of semantic hierarchy for representing images, which we are trying to do for 3D. But a big problem for doing this in 3D is that you do not have a semantic loss. So to actually recover the full signal, the FlexTalk paper says that representation alignment, or REPA for short, is actually very useful to bias the decoder to follow semantic order. And doing this for 2D is actually simple because we have very strong vision foundation models for images, such as DINO or even diffusion features. But there is no actual equivalent semantic loss or like a 3D foundation model, which gives us semantics for 3D, right? So how do we get semantics for 3D? So since there is no equivalent for 3D, one process is actually that we can decode from the latents, get back the 3D, and then render it. But this is actually computationally expensive. So what we mean is that we have this nice semantic supervision, which is quite possible, where we have these 3D latents, we can decode them back, we can do multi-view rendering and then run them through DINO and get the semantic loss back in. But the problem is that this is a very expensive process. First of all, doing the decoding to go from the latents back to the complete 3D shape is quite completely expensive. And when you add the multi-view rendering and again doing the DINO features, this actually becomes computationally quite explosive towards the end. So instead of doing that, we come up with relational distance alignment. And essentially, this means that we are going to get the 3D latents in, but we are going to do so without any kind of rendering. So what we really need to get semantics in for 3D is that we need a loss which says that if we are trying to generate a cap, we just need a loss which says that this is semantically closer to a cap, not necessarily that this is similar for the 2D space of how far it is. So for example, if DINO says that a pumpkin and a car are 5 kilometers apart in the latent space, we want to capture that in. So we are going to have the 3D latent space, and we're going to restructure this 3D latent space by reorganizing this space internally to follow the interdistances of alignment. So to follow the interdistances of DINO. So if DINO says that a bottle and a car are 7 kilometers, we're going to restructure the 3D latent space to follow those relationships which are captured by DINO. So what essentially this gives us is it helps us to bring in semantic relations into a highly geometric space. So in this image that you have, you see this quadrilateral, which is reorganized into a tetrahedral structure. So it essentially keeps all of the geometric properties of decoding the latents the same, but it does modify the 3D space itself so that the semantic relationships are captured. And this is quite important because we are not trying to actually predict DINO features. What we are trying to actually get in is the semantic relationships which is captured in DINO, but we just want the same in 3D. And we want this 3D loss to be a direct replacement of DINO so that we do not need to render anymore. And doing this is actually quite possible with contrastive losses. So over here we use InfoNCE. So we use DINO as a teacher to say what are positive samples and negative samples. So given a query, let's say an aeroplane, we can use DINO as a teacher to cover a large set of objects and find semantically close objects. So it will try to find similar planes, and maybe somewhere along the line it has some helicopter which is maybe somewhat similar, may not be fully similar, and they will capture a lot of negative samples, which can be very unrelated objects. And using these set of mind examples from DINO, we are performing contrastive loss in a self-supervised manner to actually train a network to reorganize this 3D latent space. So once we have these positive and negative samples, we can use InfoNCE loss to train the network. And the second thing that we want to have is that we want to capture the similarity matrix of DINO. Because if you only mine positive samples and negative samples, we're actually missing a lot of the rich information which is captured towards the middle, let's say, what are somewhat similar objects, not necessarily extremely similar. And to get this in, we do not necessarily want to directly predict the similarity, such as the cosine similarity of DINO, because the 3D modality and 2D modality are completely different. So these distributions are different inherently. So instead of trying to directly predict the DINO similarity matrix, we are going to z-score them and then try to predict these values. And the third thing that we want is that we want a spatial structure distillation loss, so that we want to capture the token-wise spatial distributions. So DINO, for example, has a patch level token, like the CLS token, which has a lot of information, somewhat information which carries mostly about the class. But there's also more information which is captured patch-wise. And this is what we also want to be capturing for our 3D loss. So we try to combine all of these three losses and try to train a 3D latent a network which essentially restructures these 3D latents to follow the relations which are obeyed in DINO. And we train this network completely in a self-supervised way by using DINO as a teacher. And once this network is trained, and this is just a simple transformer network, we actually can pass the 3D latents as input directly. And we no longer need to render anymore. So coming back to this architecture, where you see the semantic extractor, this is where we are going to place our loss function. So once we train our 3D semantic loss in a self-supervised way, we can actually freeze the weights and directly put this here. And then our network can actually try to put semantics back into the hierarchy when we are going to train our network to follow the semantic ordering. Yeah. So once our network is trained, we can actually get recognizable shapes from as low as 1 or 4 tokens. You can see some examples here where simple objects are actually captured quite well, even with a very low number of tokens, such as this wheel. And on the bottom right, you will see this mountain with a face on it, which is etched into it. And you can see when we have a 1 token of very few tokens, this entire face is actually missing because it is not common for a mountain to have a face. But with higher level of geometric detail, we see that this is possible. And this is exactly what we expect from a semantically increasing order. And once we have this space, we can train an AR network on this lost latent space to generate tokens in an AR native way. And for this, you can use any autoregressive architecture of your choice. We use LlamaGen in this case, and because we want our generator to be conditional, we use OpenClip to go from image to 3D. And we show some examples with 128 tokens. But since our architecture is a flexible one, it can even generate tokens from as low as 1. So with an AR model, we can always stop anywhere we want. So we can stop as low as 1 token or 4 tokens. And for some comparison with other works to show that we are not just like economically advantageous with low number of tokens, but also with token dimension. Because with other architectures such as Llama Mesh or Shape LLM Omni, the token dimension is also very large. Whereas for us, this is quite low at 32. So the total, the total footprint is actually just around 4,000, but it can be extremely high into millions for other architectures. And you can see some results on the right as well of the difference in quality of ours versus other methods, even though we are operating at a much lower token budget. And this is for some evaluation on the tokenization reconstruction, where we compare our tokenizer against OGPT and Vertex region. We see that we have higher scores across the board. And it's the same for our autoregressive model as well. We see higher FID and DINO similarity scores. And interestingly, we can actually get shape retrieval for free. So over here, we show an example of a submarine, which is actually shaped like a shark. So if you try to perform this shape retrieval directly in the 3D latent space, which is highly geometric, so in this case, the triplane latent space, the query, because it looks like a shark, it will always fetch objects which are sharks, because this is just focused on geometry. But DINO is actually semantically smart, so it actually is able to fetch other submarines. But once you map those triplane latents into our RIDA latents, because this is just a geometric transformation in the latent space, our RIDA space is actually quite smart enough to actually fetch submarines at the end, even though the query is shaped like a shark. And we see higher scores for shape retrieval across the board when comparing against the raw geometric triplane latent space. And in the middle, you'll see that we also have a comparison against the regression. By the regression, we mean if we train a network to directly predict DINO features. And that does not work well at all, as you can see. And here we show some ablation for our network, which is trained with and without RIDA. Particularly for complex objects, we see that RIDA is actually even more important to the network to help get semantics in, particularly for low budgets. So for example, if you have a single token and you're trying to generate a cap, at one token, you can actually get the class completely wrong. Over here, it tries to generate a cup and not a cap. And so on with some of these other examples where the class itself can be unrecognizable or wrong. So this is our project webpage. And yeah.